Hello guys, welcome back. I'm your friend in Saxo. Today let's start our first day of learning with mathematics. I shall start it from the most basics, and if we can say if we can get it right. So let's go from the first one, addition and subtraction.
Welcome to the presentation on basic addition. I know what you're thinking, Sal. Addition doesn't seem so basic to me. Well, I apologize. Hopefully by the end of this presentation or in a couple of weeks it will seem basic. So let's get started with I guess we could say some problem. Let's say I start with an old classic. 1 plus 1. And I think you already know how to do this, but I'll kind of show you a way of doing it in case you don't have this memorized or you haven't already mastered this. You say, well, if I have one, let's call that a avocado. If I have one avocado and then you were to give me another avocado, how many avocados do I now have? Well, let's see, I have 2 avocados. So 1 plus 1 is equal to 2. Now, I know what you're thinking. That was too easy. I like the avocado. What is 3 plus 4? So this is a more difficult problem. Well, let's stick with the avocados. And in case you don't know what an avocado is, it's actually a very delicious fruit. It's actually the fattiest of all the fruit, even if you eat it. So let's say I have 3 avocados. 1, 2, 3. Right? 1, 2, 3. And let's say you were to give me 4 more avocados. 4 in yellow, so you know the ones you're giving. 1, 2, 3, 4. So how many total avocados do I have now? 1, 2, 3, 4, 5, 6, 7 avocados. So 3 plus 4 is equal to 7. And now I'm going to introduce you to another way called the number line. And actually, I think this is how I do it in my head when I forget. I don't have the number line. I just write all the numbers in order, and I go high enough just so all the numbers I'm using are kind of in it. So you know the first number is 0, which is nothing. Maybe you don't know, but now you go to 1, 2, 3, 4, 5, 6, 7, 8, 9, going 11. So we're saying 3 plus 4. So let's start at 3. So I have 3. And we're going to add 4 to that 3. So all we do is we go up the number line, or we go to the right on the number line, 4 more. So we go 1, 2, 3, 4. Notice all we did was just increased it by 1, by 2, by 3, by 4. And then we ended up at 7. That was our answer. We could do a couple of different ones. We could say, what if I asked you what 8 plus 1 is? 8 plus 1. You might already know it. Plus 1 is just the number line. You start at 8 and you add 1. 8 plus 1 is equal to 9. Let's do some harder problems. And just so you know, if you're a little daunted by this initially, you can always draw the circles. You can always do the number line. And eventually, over time, the more practice you do, you'll hopefully memorize these and you'll do these problems in like half a second. I promise you. You just got to keep practicing. Let's say I want to draw the number line again. Actually, I have a line. Okay. So it's looking line. Feel bad to erase. 2, 3, 4, 5, 6, 7.
You know what? I start to feel that this is a little bit boring. So I would like to increase the speed for a little bit. Let's say 2 times, something like that. I guess that would be enough for us. Now let's go ahead.
9, 10, 11, 12, 13, 14. Let's do a hard problem. We'll do it in different colors now. 5 plus, if you want, you could pause the video and try this. You might already know the answer. And the reason why I say this is a hard problem is because the answer has more numbers than figures. So you can't necessarily do it on here. So let's get started. I'm going to ignore the phone because you're more important. So, okay, let's start at the 5. So we start at the 5, and we're going to add 6 to it. So we go 1, 2, 3, 4, 5, 6. At 11. 5 plus 6 is equal to 11. I'm going to ask you a question. What is 6 plus 5? Well, we're not going to see that. Can you switch the 2 numbers and get the same answer? Well, let's try that. I'm going to try a different color so we don't get all confused. So let's start at 6, right? Ignore the yellow for now and add 5 to it. 1, 2, 3, 4, 5. We get to the same place. And I think you might want to try this on a bunch of problems, and you'll see it always works out. That it doesn't matter what order you add. 5 plus 6 is the same thing as 6 plus 5. And that makes sense. If I have 5 avocados and you give me 6, I'm going to have 11. If I have 6 avocados and you give me 5, I'm going to have 11 either way. Let's do a couple since this number line is so nice, I want to do a few more problems. I use it, I'm sure. Let's see. What is 8 plus 7? Well, if you can still read this, 8 is right here, right? We're going to add 7. 1, 2, 3, 4, 5, 6, 7. Hopefully, that gives you a sense of how to do these types of problems. And more than, I guess, this, and you're going to learn multiplication a little bit. These types of problems are, when you're getting started off in mathematics, these kind of require the most practice, and to some degree, you have to start memorizing them. But over time, when you look back at it, I want you to remember how you feel while you're watching this video right now, and then I want you to watch this video in like 3 years, and remember how you felt when you're watching it now, and you're going to be, oh my god, this was so easy, because you're going to learn so fast. So anyway, I think you have an idea. If you don't know the answer to any of the addition problems that we give in the exercises, you can press the hints, and it'll draw circles, and you can just count up the circles. Or if you want to do it on your own so you get the problem right, you could draw the circles, or you could draw a number line like we did. You might be ready to tackle the addition problems. Have fun.
This one is easy. So basically what he is doing is to teach us how to do the subtraction or not subtraction. How to do the addition with a number line.
Subtraction. A little bit of review of if I said 4 plus 4 plus. Well, there were a couple of ways that I had 4. 1, 3, 4 lemons for breakfast. And let's say I had another 3 lemons for lunch. 4 plus 3 as how many total lemons did I have? I'm adding 3 to what I have. 3, 4, 5, 6, 7. So I had a total of another way that is 9. brought in yellow, let's say that's if I start, draw 4, 5. This is saying, well, we're on the number line. We started adding increase along the number line by 1, 3, 7. So you could say if I have 4 and I increase 4 by 3, I also do plus minus 3. What is that? What is 4 minus subtraction or minus opposite of addition? Or you're adding addition, but that's 4 lemons and then I had subtraction. This example, if I started with 4 lemons, I had 4 lemons on a plate. Instead of adding 7, I'm going to take 3 away. Maybe I'm taking away 3 from this 4. Let's say this one goes away, this one goes away. How many lemons would we have that I have? 1. Another way to do that, let's draw the same lemon-colored line. All row 4, 5, 7. Of course, the number line is higher than that. So they're starting at 4 lemons. Added to the right 4, space to the right 5. That was 1 more. 5 to 6 was 2 more. Now we're taking away lemons. So we take away 1, we get to 3. Take away 2, away 3, right? Add 1.
You know what? I still think that this is too fucking basic. I probably don't want to go through with it. Let's say at least I don't want to deal with addition or subtraction some kind of things like that. I don't want to deal with it. Probably we should go to the fractions because that's more complex than other math concept. So let's get into it.
Sense. So now I have 8 equal parts. 8 equal parts. And now I'm going to select exactly one of them. And that'll represent 1/8. And I could select any one of these, but I'll just do this one to show you it does not have to be necessarily the first one. So once again, this square right over here that I'm shading in red represents 1/8 of the whole. Now let's look at a few more examples where I've shaded them in ahead of time. And what I want you to do right now is pause the video and either in your head or on a piece of paper, write down, if you consider this purple thing the whole, what fraction does this red part represent? If you consider this blue part the whole, what fraction does this red part represent? If you view this yellow triangle as a whole, what fraction does this red part represent? And so I encourage you to pause the video now. Well, let's look at each of these. So in this case, for this rectangle, we have 3 equal parts, and we've shaded in one of them. So this red rectangle right over here represents 1/3 of the whole. Now over here, in this kind of pie-looking thing, this circle-looking thing, we have 1, 2, 3, 4, 5 equal parts. 5 equal parts, and we have shaded in one of those 5 equal parts. So this little slice of the pie, this represents 1/5. This right over here is 1/5 of the entire fraction, or of the entire pie. Now this one's interesting. You might be tempted to say, well, I've got 4 parts and then I've shaded in 1. That must represent 1/4. But remember, it needs to be 4 equal parts. And it's pretty clear looking at this that this part right over here is not equal in size to this part right over here or this part right over here. These are not 4 equal parts. So we cannot say that this is 1/4 of the triangle. So you cannot say that.
So I still think this is kind of basic, but for the fraction, all we need to know is just 2 parts. I guess it will be demonstrated inside of this video.
To identify the numerator and denominator in the fraction 3/4, or 3/4. So let's rewrite this just so it's nice and big. So let me just write the fraction. So we have 3 over 4. 3/4. Now, they want us to identify the numerator and the denominator. The numerator. So the numerator is just the number on top. So the numerator is the 3 right there. And then they want us to find the denominator. The denominator is just the number on the bottom, the 4. So if they say, what's the numerator? 3. What's the denominator? 4. Just the number on the bottom. They could have just called this the number on the bottom. They could have just called this the number on top. Now to think about what this represents, what this fraction represents, you can think of it of 3 out of 4 pieces of a pie. That's how I think about it. So you can imagine the denominator tells us what are we taking a fraction out of, or how many pieces are there. So let's imagine a pie like this. So we could draw it like, well, we could draw it as a square pie. So we could draw it as a square pie. So this is what the denominator represents. This is what the number on the bottom represents. And then 3 says we are representing 3 of those 4 pieces. So
okay, that's enough. So
this 3 tells.
So let's say if you ask me what this is, so the number on top is the numerator, and the number button on the bottom, the number under the button is the denominator. It's just a line for this fraction. So again, 3 is the numerator, 4 is the denominator. Okay, only if you remember that, that's enough for us. So let's go to somewhere else. We don't need to actually go through all those fraction courses because we don't need that. We are an adult, not a child anymore. So we probably could go to a higher level than this, and we probably could just go from the pre-algebra, and that would be enough for us. So let's just let's go through it. Arithmetic properties. All right.
Find the place value of 3 in 4,356. Now, whenever I think about place value, and the more you do practice problems on this, it'll become a little bit of second nature. But whenever I see a problem like this, I like to expand out what 4,356 really is. So let me rewrite the number. So if I were to write, and I'll write it in different colors. So 4,356 is equal to, and just think about how I just said it. It is equal to 4,000 plus 300 plus 300 plus 50 plus 50 plus 6. And you can come up with that just based on how we said it. 4,356. Now, another way to think about this is just like saying this is 4,000s plus, or you could even think of and, plus 300s plus 50. You could think of it as 5 tens plus 6. And instead of 6, we could say plus 6 ones. And so if we go back to the original number, 4,356, this is the same thing as 4. I'll write it down. Let me see how well I'll write it up right. This is the same thing as 4,000s, 300s, 5 tens, and then 6 ones. So when they ask what is the place value of 3 in 4,356, we're concerned with this 3 right here. And its place value, it's in the hundreds place. If there was a 4 here, that would mean we're dealing with 400. If there's a 5, 500s. It's the third from the right. This is the ones place. That's 6 ones, 5 tens, 300. So the answer here is it is in the hundreds place. It is in the hundreds place.
So 100 place. That's good. Let's go to the next one.
What we're going to do in this video is think a little bit about place value tables, and sometimes they're referred to as place value chart. In previous videos, we've already talked about the idea of place value, and a place value table or a place value chart is just a way to say how much value we have in each place in a very, very clear way. So here they say use the place value chart to write 60,229. And this is the place value table or place value chart right over here. They say enter a digit, one digit number in each box of the place value chart. So really all they're saying is how many 10,000s do we have? How many thousands? How many hundreds? How many tens? And how many ones? And like always, it's always a good idea to try to have a go at it before I do it with you. So why don't you do that? Why don't you pause the video and on a little piece of scratch paper say how many 10,000s are in 60,229? How many thousands are there? How many hundreds? How many ones? All right, now let's do this together.
Actually, I could give you the idea. How many thousands? Or 10,000s. How many 10,000s? Let's say it's probably 6. How many thousands? No, probably 0. And how many hundred? Maybe 2. How many tens? 2. How many ones? 9. Okay, I guess this is the answer of mine.
Sure. So we could start at the left in the 10,000s place. This is the ones place. This is the tens place. Let me do that a little bit neater. So this is ones, tens, hundreds, thousands, 10,000. So we can see that we have 6 10,000s. So all we would do is say, we'd put a 6 there. We have 6 10,000s. And then how many thousands? Well, that would be one place over to the right. This is interesting. We can see very clearly we actually have 0,000. So 0,000. You might say, hey, when you say this out, you say 60,229. Don't we have 60,000s? Well, you already accounted for that in the 6 10,000s. 6 10,000s is 60,000, but just in the thousands place, you have none. And then we move on to the hundreds place. You can see very clearly we have 200. And then we can go to the tens place, and I've written over it a little bit, but we have 2 10. And then last but not least, we have 9-1. And we're done. And so the whole point of this video is to just get you comfortable with this type of format, with a place value table or a place value chart. And all it is a way of really clearly writing out how much value you have in each place in a number like this.
Right, 645,584,462 in standard form. So let's tackle this piece by piece. So the first part, we have 645 million. 645 million. So let's think about that. So we have 645, but it's not just 645. We have 645 millions. So we could view that as 645 times 1 million. 1 million is 1 followed by 6 zeros. So this piece right here is this right over here. That is 645 million. And what is that when we write it out? If we were to multiply this out, this is equal to, it would be 645 times this 1 with 6 zeros behind it. So this would be equal to 600, I'll write it like this. This is equal to 645, and then we have our 6 zeros. 1, 2, 3, 1, 2, 3. That's just this part of the number. And I'm going to do it kind of slow and do all of the different parts of the problem. But once you get some practice, you'll find that these are a bit second nature, and you won't have to go through all of these steps. You'll just be able to write the number. Now let's move on to the next part. We have 584. We write that down. Actually, let me write it like this. I'll write it like this. 584,000. 584,000. So let me write 1,000. So 584,000. So it's 584 times 1,000. And what's that going to look at? So that's this whole part right here. So 584 times 1,000 is equal to what? Well, it's going to be 584 with 3 zeros behind it. Or you could view it as 584 times the 1, and you're going to have 3 zeros in the final answer. So it's going to be 584,000. You have our 3 zeros at the end. 584, 3 zeros. So that's that part. And then finally, we have 462. 462. And that's just 462 straight up. You can view it as 462 1. So then you just have 462, which obviously equals just 462. Now, our number is all of these combined. It is 645 million and 584,000 and 462. So one way to think about it is that you could add these three numbers. If we were to add them, we get 645 million, 584,000, 462. 462. Now I said it'll become a little bit of second nature to you in a little bit. And the way to think about that, the easiest way to think about that is millions will have 6 zeros behind them. Thousands will have 3 zeros behind them. And just regular numbers have no zeros behind. So what you can do when you kind of want to learn second nature, you'll just look at the 645 million. So you'll write 645, and you'll kind of keep in the back of your mind that you're going to have 6 more digits to the right of this. And then you say 584,000. So then you have your 584,000. So then you write that down, 584,000, keeping in mind that you're going to need 3 digits to the right of that. And so if they didn't tell us 462, we would just put 3 zeros here. And that would also fulfill the 6 zeros we need behind 645 million. But then they tell us 462, so we just write that right here, 462.
Well, that's intuitive.
Write 14,897 in expanded form. So let me just rewrite the number, and I'll color code it, and that way we can keep track of our digits. So we have 14,000. So 1, I don't have to write. Well, let me write it that big. 14,897. Let's see, I already used the blue. Maybe I should use yellow, and 97 in expanded form. So let's think about what place each of these digits are in. This right here, the 7 is in the ones place. This is in the ones place. This is in the ones place. The 9 is in the tens place. The 9 is in the tens place. This literally represents 9 tens, and we're going to see this in a second. This literally represents 7 1. The 8 is in the hundreds place. This is in the hundreds place. The 4 is in the thousands place. It literally represents 4,000. So this is in the thousands place. And then the 1 is in the 10,000s place. And you see, every time you move to the left, you move one place to the left, you're multiplying by 10. Ones place, tens place, hundreds place, thousands place, 10,000s place. Now let's think about what that really means. If this 1 is in the 10,000s place, that means that it literally represents. So this 1 literally represents. I want to do this in a way that my arrows don't get mixed up. Actually, let me start at the other end. Let me start with the 7 represents. The 7 literally represents 7 ones. 7 ones. Or another way to think about it, you could say it represents 7 times 1. All of these are equivalent. It represents 7 ones. Now let's think about the 9. That's why I'm doing it from the right so that the arrows don't have to cross each other. So what does the 9 represent? It represents 9 tens. You could literally imagine you have 9 actual tens. You could have a 10 plus a 10 plus a 10. Do that 9 times. That's literally what it represents. 9 actual tens. 9 tens. Or you could say it's the same thing as 9 times 10. Or 90. Either way you want to think about it. So let me write all the different ways to think about it. Or 90. It represents all of these things. 9 tens, or 9 times 10, or 90. So then we have our 8. Our 8 represents, we see it's in the hundreds place. It represents 8 hundreds. 8 hundreds. Or you could view that as being equivalent to 8 times 100. 100, not 1,000. 8 times 100, or 800. That 8 literally represents 8 hundreds. 800. And then the 4. I think you get the idea here. This represents in the thousands place. It represents 4 thousands. 4 thousands, which is the same thing as 4 times 1,000, which is the same thing as 4,000. 4,000 is the same thing as 4 thousands added up. And then finally, we have this 1, which is sitting in the 10,000s place. So it literally represents 1 10,000. 10,000. 1 10,000. Or you could imagine it. You could imagine if these were kind of chips, kind of poker chips, that would represent one of the blue poker chip. And each blue poker chip represents 10,000. I don't know if that helps you or not. And 1 10,000 is the same thing as 1 times 10,000, which is the same thing as 10,000. So when they ask us to write it in expanded form, we could write 14,897 literally as the sum of these numbers, of kind of its components. Or we could write it as the sum of these numbers. Actually, let me write this. This top 7 times 1 is just equal to 7. So 14,897 is the same thing as 10,000 plus 4,000 plus 4,000 plus 800 plus 800 plus 90, the 90, or 90 plus 90 plus 7 plus 7. So you could consider this expanded form, or you could use this version of it. Or you could say this is the same thing as 1 times 10,000, depending on what people consider to be expanded form, plus 4 times 1,000, plus 8 times 100, 8 times 100, plus 9 times 10, plus 9 times 10, plus 7 times 1. Roll to the right a little. Plus 7 times 1. So either of these could be considered expanded form.
You know what? This is kind of boring.
What we're going to do in this video is get some practice writing reasonably large numbers in different ways. How would you write this number? Sure, if you're how many tens? 600.
Yeah, as I said, this is kind of boring. It's like everybody could do. But that's also the amazing part for the Khan Academy, because it provides some very, very basic materials for the mathematics. So it's easier. It's very easy for those kids to grab up and increase their ability of mathematics. So let's go to the next one. I probably do not need to do this anymore.
Literally represents 10,000.
Yeah, it's like my second nature for all those kind of problems.
The 10 times value of the first 7. 10 times less. 25,400. We're going to take 25,430 and
What is 7 hundreds times 10. Well, let's focus first on this times 10 part of our expression, because multiplying by 10 has some patterns in math that we can use to help us solve. One pattern we can think of when we multiply by 10 is if we take a whole number and multiply it by 10, we'll simply add a 0 to the end of our whole number. So for example, if we have a whole number like 9 and we multiply by 10, our solution will be a 9 with 1 0 at the end, or 90, because 9 times 10 is the same as 9 tens, and 9 tens is 90. So let's use that pattern first to try to solve. Here we have 7 hundreds, so 7 times we have 100, or 700, and we're multiplying again times 10. Use this pattern over here, our solution will add a 0 at the end. So if we had 710 times, we would have 700 with a 0 on the end, or 7,000.
This is still too basic. Let's go to the next one.
We have 4,500 equals 3 thousands plus how many hundreds? Question mark hundreds. So let's write this left-hand side, but I'm going to write it out in terms of thousands and hundreds. So I'll write the thousands in orange. So this is equal to 4 thousands, which is the same thing as just 4,000 plus 500. You could also view as 500s plus 500. So this is the left-hand side. Now let's look at the right-hand side. We have 3 thousands, so it's 3 thousands. Now let's not even look at this right now. Let's just think about what do we have to add to this right-hand side in order to get the same thing that we have on the left-hand side. Well, if you compare the 3,000 and the 4,000, you see you have an extra 1,000 over here. So let's add an extra 1,000 on the right. So we're going to add one extra 1,000. And now we just have 3,000 plus 1,000. This makes it the 4,000. But then, of course, we also need another 500. So we're going to need plus a 500 right over here. So in order for these two things to be equal, we need to say 4,000 plus 500 is equal to 3,000 plus 1,500. Now, the way they've set this up, we need to express, so it almost looks the same. On the left-hand side, this is 4,500. So this right over here, this is the same thing as 4,500. This is this right over here. And on the right-hand side, we have 3,000s. So that's this right over here. That's the 3,000s. And then we just need to express this as hundreds. So 1,500, this is the same thing as 15 hundreds. So let's rewrite everything. We can rewrite this as saying 4,500, just to get the exact same form that they wrote it over there. So we could write 4,500 is equal to 3,000s plus, now we have to just write this in terms of hundreds. Well, this is 15 hundreds. Literally, if you took 15 times 100, it's going to be equal to 1,500. So this could be viewed as 1,500. So plus 15 hundreds. So in this situation, the question mark is equal to 15.
All right. Yeah, I still think these things are just two basics. Even about this, writing the whole number, I guess Python could do the same thing. Order of operations, probably you think this is very important if you didn't know any math or the programming language, but if you do, you would know that it's just like what the Python operators would do. About the rows of addition or subtraction or multiplication or division kind of stuff, we have already learned in our past education experience. The reason that you do not know is probably the rational and irrational numbers. So we could have a check on those two videos. Let's go with this one.
Which of the following real numbers are irrational? Well, irrational just means it's not rational. It means that you cannot express it as the ratio of two integers. So let's see what we have here. So we have the square root of 8 over 2. So square root of 8, if you take the square root of a number that is not a perfect square, it is going to be irrational. And then if you just take that irrational number and you multiply it and you divide it by any other numbers, you're still going to get an irrational number. So square root of 8 is irrational. You divide that by 2, it is still irrational. So this is not rational, or another way of saying it, it is irrational. Now you have pi, 3.14159. It just keeps going on and on and on forever without ever repeating. So this is irrational, probably the most famous of all of the irrational numbers. 5.0, well, I can represent 5.0 as 5 over 1. So 5.0 is rational. It is not irrational. 0.325. Well, this is the same thing as 325 over 1,000. So I can clearly represent it as a ratio of integers. So this is rational, just as I could represent 5.0 as 5 over 1. Both of these are rational. They are not irrational. Here I have 7.777777, and it just keeps going on and on and on forever. And the way we denote that, you could just say these dots that say that the 7s keep going, or you could say 7.7, and this line shows that the 7 part, the second 7, just keeps repeating on forever. Now, if you have a repeating decimal, in other videos we'll actually convert them into fractions, but a repeating decimal can be represented as a ratio of two integers, just as 1/3 is equal to 0.333 on and on and on, or I could say like this, I could say 3 repeating. We can also do the same thing for that. I won't do it here, but this is rational. It's not irrational. 8 1/2, well, that's the same thing. 8 1/2 is the same thing as 17 halves, so it's clearly rational. So the only two irrational numbers are the first two right over here.
Okay, it at least tells us that what is a rational number and what is an irrational number. And that, I guess that's enough for the pre-algebra part, I guess. Or maybe not. Let's go back for a little bit. Oh shit. We need to let's go to the pre-algebra. Oh, this is basically the first part of the arithmetic properties. Actually, we have already done this part of learning. So in the next video, we will go to the factors and the multiplies, and it will not take long since we have already learned those things in our mother tongue, or yeah. We have already learned those stuffs before, but for now, all we have to do is to learn it again with the English language. Okay, that's today's learning. I will see you in the next video. Bye.